I'm presenting work on a field that is a little bit behind in technology, that's landscape design. Even we was once on the forefront when I was thinking about GIS system, but in the recent years, we suffer a lot from the complexity of our work. And before we coming to the exciting part, I always have the bitter pills to lower the expectations. And I would like to start with what I already quoted yesterday in the discussion from Mihai Nadin, a computer scientist and philosopher, now at the University of Texas in Dallas. And it's in German even more pregnant than in English, where few missed, few missed, who measures much, measures garbage. And it's the question about what and why we are measuring and how we're getting out of data information and how we're getting meanings into the data. And the question, are we doing data collection because we can? Are we doing it while we need it? And what data we need, and what do we making AI models because that are easy to do, or do we doing AI models because they're answering important questions? And that comes to the second one. That's a quote from Bruce Cameron. It's sometimes quoted to Albert Einstein, but it's actually not from him. Not everything that counts can be counted, and not everything what been counted counts. And I think the last one is garbage in and garbage out from Fuchsam, famous IBM computer scientist. That is about the quality of our data and who is responsible for this data and their quality. And as it was very early discussed between the first computer between Charles Babbage's machine, you can't expect good results from bad data. And but now I would like to introduce who is working on all this, and that's mostly me, Andreas Luka. I'm working in San Jose. I'm working as a BIM consultant, and I'm more from the practical side and how to get all this knowledge into a day-to-day use in an office. And the more research part is based in China at Tsinghua University with my partner, Professor Goyong. And especially for the BIM trees, we have also some partners in Switzerland. We have Jardin Suisse, that's the Federation of the Swiss Gardeners, that are delivering a lot of data for us. And with Lukas Schmidt, we are developing now this as to a commercial product. And Professor Peter Pacek, who's teaching BIM in Rapperswil for landscape architects, who was one who is initiating BIM trees and started with the students to using them, testing them, and having a great feedback on this product. And we started with a very fundamental question when we used Peter used Rivet for teaching, and he was complaining about the trees that are coming with Rivet or from other third-party suppliers. They're very based on visualization and aesthetics, talking about seasonal and life cycle, getting older, and they're often very detailed. And we need sometimes very generic trees on very early design stage, like we see on these pictures. That's an landscape rendering of a generic tree. And in BIM, we need completely other things. We need trees that are complete. They have roots, because most conflicts are in the underground with sewer lines, cables, and so on. We need trees that are parameter based, so we can manipulate them on the computer. We can let them grow. They have to be functional, so they need really to represent the form that this tree is over the time. We all know we by ourselves growing differently in age. First we're growing in height, then in height, and trees are quite similar on this one. And they need to be interoperable. We can't expect that everybody has the same tool in his toolbox that I'm using in my office or in my practice. And we need to be also able to transfer our information into completely other systems, because not every question can be answered or solved with BIM. And the trees are based on two general ideas that we put together. That is, one's an asymmetric hull model developed by Cascati for forest science using measuring light and in forest environments, but he can represent with this kind of model with only 6 parameters, 6 points and 2 form parameters, a huge variety of crown forms with a very small memory footprint that makes it possible to having thousands of trees in one model. And we could show that we could adapting this same model to roots. And the second one is finding formulas or models that can describe growth of a tree or other plants over a whole life cycle. So if we see many equations are very limited in their boundary boxes in when they are valid, like in the middle where we have this nice almost linear growth, but on the beginning, on the end, the growth is very different. And this model is also suitable for many different parameters of a tree. So we can simulate the development of diameter, breast height, of height, of spread of the tree, but also for height of largest crown radius, all this what is needed to describe a tree properly. And it's also very widely used in forest science for forest measurements and yield tables. So we have a lot of well comparable data and good knowledge how to solve this as a regression with it's a non-linear robust regression model what we are using to finding this growth parameters. So we can see, so we try to describe this tree with really with parameters that can be also compared to real existing trees. And we mostly doing this on a very simple graphical way, doing splines around the trees, and then we translating this splines into super ellipses because it is much more efficient to store and to manipulate than splines. And as we mentioned before, we fitting the growth curve with mostly with R, robust nonlinear regression, but it could be done in Python. A couple of packages are available, and we're using special reparameterization of these formulas. We have a very small, simple one for writing our code, and we have a reparameterization that is more comparable with data that we know from tree nurseries, like what is the point of the strongest growth, that's the inflection point of the curve, what is the maximum height of a tree, that's the asymptote of a curve, and so on and so on. We have there a special paper, and I also have a bigger blog over this topic on my website. But you also have to see that's our empirical models. So often the best fitting curve is not the right curve. So we found that sometimes curves starting not at the right point, like diameter at breast height can't start at 0 because breast height you only have after 4 or 5 years of a tree. So a model that fits to 0 isn't correct. So that's a problem what we facing with all empirical models and people working in digital twins, where we go to lower order models and facing actually the same problems. I would like to give a very short demo by stopping this screen. I think you can see now left BIM software, Revit, and right you see Enscape, and you see a first glimpse of this trees what we use. So you can see in BIM they have a root system. They're representing, these are very generic trees for urban design studies. So and with very simple textures for really large areas, small scale design. And they're not very exciting yet. The exciting comes when we changing them. I close the Enscape for this one because it's slows down the computer a little bit. So I want to open this one and I want to get my properties back. And this tree doesn't have growth yet. It's a, as I say, a generic trees, but now we're exchanging this tree to a tree that really have these capabilities. So let's exchange this one to, let's say, a Tyrigodata greenspire. And you see it's very small because it is the site how it's getting delivered onto the planting site. And we are giving the global parameter on it that gives us the age. And by manipulating these global parameters, we can manipulate the tree size and his development very simple and efficient. Let's change up, move this over to this window. Let's say instead of a 25 years after planting, I want to see this tree a little bit earlier. I want to see it 5 years after planting. 10 years, or whatever I want. And let's change this tree also. Here we go. And let's load one to see how this is organized. So that's our rivet families. And that's our the trees that are available for the students. And let's find, let's use an Arza campestre. And now we have the complete specifications from the Swiss tree nurseries. Whatever kind of tree you can buy in the tree nursery is in our database and can be accessed here. And they have start values, so we know on which size the tree is coming to construction site. And from there, we're starting our growth equation. Let's get a little bit bigger one. Let's get this, yeah, getting one with a root ball and getting a quite big gird. Okay, here we go. Okay, and we're giving this tree also the same age like, or the same time since planting like the other trees to adjust them simultaneously. So this helps us really in clash detection because they are actually solids. So we can use them in Navisworks or whatever software people are using for doing their BIM clash detection. And the growth are also, is also related to the roots. So we see when the tree is getting bigger, the root system is getting bigger. And we can find a couple of clashes, what is normally not visible if I draw or model the tree only in one size. Mostly the standard is that we have a 25 to 30 years old tree in our drawings and models, but we can detect conflicts that are coming maybe much later because the tree is growing very big or the root going deeper and hitting the underground car park. So we need to be aware how we're protecting the root system against damages when cable need to be repaired, or another way around, how we protecting building elements against aggressive root systems. That's how we started, and we are developing this now into product. But as you can see, there's a big empty space, and this also didn't show up in the Enscape because it can't show up in the Enscape because it's a point cloud. Let me go to, let me quickly go to my view user interface and get my project browser on. So we can see over here, we have a LiDAR point cloud. And you already can see in this very simple BIM model that LiDAR point clouds have a fundamental problem. There are points, they are not solid objects, they are not meshes, they don't create shadow, that can't be, they're very limited in analysis. So let me have, going to back to the presentation to talk about this on a little bit more. Start from current slide. So what we are doing is, or what we are trying to achieve is changing this point cloud into solid models. That's our QSM, quality structure models, or quantity structure models, sorry. And you can see they're already casting shadow, but they're highly detailed and also bringing computational problems. They have a very high computational costs, but they can be very well analyzed. We can tracing back the development of the trees over years. And the next step is to simplify them to envelope models, like we're using here also the Cascati model based on this point on the bottom top and 4 points on the periphery on the largest crown radius to creating this model. And now we are able to using also clash detection against existing trees. The process is that we have a special software coming from forest science called CompuTree with a simple forest plugin that are basically algorithms based on the point cloud library for clustering points after we having still a lot of manual work to get some noise and disturbance away, as very critical are lampposts that really disturbing the algorithm. And I would like to show this in a small video. Let me go out of the presentation and start the video.
Andreas, just confirming we have a minute left or so now.
Can you hear it?
No, we cannot hear, but we can see it.
Okay, then I'm talking to it. So this is a small group of trees as derived from terrestrial laser scan, and it's a bigger area. And we separate them in groups to process them faster. And there we need to start to clean them up, especially there are a lot of bicycles, persons, and yeah, especially lampposts. They are very critical. And we have here a smaller problem. We don't have enough ground. A lot of algorithms are based on height to the ground for identify special points. So we do the manual correction on it. So now is the prepared point cloud there. And now we start the process chain on the left side. And the first step is finding the ground points. So the ground points are very simply, we make little squares out of this. We're finding the lowest point in each square. And then from there, we're starting to find points that are very close to this level. We also removing the collar of the trunk because that's normally not a cylinder, and there we're making special processing there. And then we try to identify a very clear area that where we know that is definitely belongs to one of the tree. And from there, we start to grouping the trees and starting with a clustering algorithm based on a Euclidean distance. And these cylinders are especially valuable for measuring and comparing trees. Then we're using some more clustering algorithm. This one is now a Dijkstra clustering algorithm, and then comes Voronoi clustering algorithm, and we can identify each tree. And then comes a very costly computational task, fitting cylinders in to this point clouds. But this gives us the opportunity to get volume out of it. And there are a couple of corrections happen during this process, like based on biological knowledge, that's called reverse pipe model. And on the end, we adding the lowest point from the tree to the ground. In this case, we simple extending it. If we have special roots collar systems, then we do this with a special fitting. And now we have a mesh, and now the video is finished. And this
Yeah,
mesh
okay.
we further
Yeah.
processing then in CAD. And let's go back to the presentation.
Andreas, just confirming we've run out of time, so
Okay,
you can
I'm hurry up.
conclude very briefly. Yeah.
Yeah. So the quantitative structure model have really one big advantage, because there are numbers that can be very well analyzed. So from there we can go from the endpoint of the twigs, we can find a concave hole, an alpha hole, and from there we deriving the Cascati hole. And this gives us the opportunity to really go in with this one to things like digital twins and generative design. So both are need lower order models in order to be trees, make them analyzable. So let's go quickly into this one. If we have time for this demo, or we're just keeping it by this picture. So here you can see analysis with Solar based in Revit on the left side, and then with tools in Revit for it's Dynamo programming environment. What this one then later feeds into an generative design algorithm to find an optimum layout of trees compared to costs. So it's a two-factor analysis optimizing with two different goals: cost minimizing and shadow maximizing. We can have a short look into it if this times allow.
Unfortunately, Andreas, I'm really sorry, we won't have the
No, no
time. It's
problem.
over 20 minutes. Yeah, so if you have one conclusion slide, we can do that. Otherwise, we'll have to
Yes,
go into the
I have a
discussion.
conclusion. Yeah,
Yeah.
I have a conclusions slide coming over here. So slide here. So we are there that we are able to build proper models as solids and mesh that can be really processed in software for design and analysis. That means that plans can be getting part of generative design tasks. We have, with reduced model complexity, a faster processing time and easier access to data. And with these models, we are also able to improve metrics for performance analysis because we can measure like woody volume and therefore carbon sequestration without cutting trees down. And but we have still a lot of gaps in our process chain. We still need to have a lot of manual tasks to interrupt in these workflows, and we still lacking tools for integrating this in our day-to-day process, and especially we are lacking generalized models for designing. So it's still a very time-consuming task to developing individual models for each design task. That's would be the end.